Quantum computing, the transition to the real world. Quantum computing is making a slow but sure transition from the realm of academic research to real-world application, with its eventual effects promising to be far-reaching. Organizations across critical sectors like finance, healthcare, and cybersecurity are now actively investing in proof-of-concept projects to explore its potential for portfolio optimization, molecular simulation, and the development of quantum-safe encryption to prepare for future threats. Classical versus quantum, a fundamental difference. The revolutionary power of quantum computing is best understood by contrasting it with the classical computers we use every day. Classical computing operates on the principles of classical electrodynamics, uses bits, which can only be in a state of either 0 or 1. Processing is sequential, performing one operation at a time. It is deterministic, meaning its outcomes are predictable. Quantum computing operates on the principles of quantum mechanics, harnessing the power of subatomic particles. Uses qubits, which can exist in a superposition of both 0 and 1 at the same time. Processing is parallel, capable of performing millions of operations at once. It is stochastic, probabilistic in nature. This inherent parallelism, along with another key quantum feature called entanglement, where the state of one qubit is intrinsically linked to another, allows quantum machines to tackle complex problems far beyond the reach of classical systems. Their computational power scales exponentially with the number of qubits, promising dramatic speedups. The architecture of quantum computing platforms, QCPs. Modern quantum computing is not a standalone process but a hybrid architecture that integrates two main layers. The quantum computing layer. This includes the core hardware, such as the quantum processing unit, QPU, which contains the qubits, and the crucial quantum classical interface that allows the two systems to communicate. The classical computing layer. This consists of the programming environment, cloud data centers, and business applications that support the quantum system. Programmers typically access these quantum processes remotely via the cloud to develop and test their algorithms. The quantum technology landscape and key players. A global race is underway, with various industry-leading organizations competing to develop and commercialize different types of quantum technology, including superconductor-based, ion trap, photonic, and neutral atom quantum computers. Key players: IBM, Google, Microsoft, Amazon Web Services, AWS, NVIDIA, Intel, D-Wave Systems, Rigetti Computing, and IonQ are among the major players pushing the boundaries. Recent milestones. IBM unveiled its 1121-qubit Condor processor and provides cloud access to its hardware. Google's 105-qubit Willow chip demonstrated exponential error suppression. Microsoft released its Majorana 1-inch quantum processing unit and an open-source quantum development kit. D-Wave built the first commercially available quantum computer and recently developed a 4,400-plus qubit system focused on optimization problems. Applications across industries. The implications of quantum computing are staggering, with the potential to solve critical problems in numerous sectors. Healthcare and pharma, accelerating drug discovery, designing novel materials, and optimizing treatment therapies. Financial services, developing advanced trading strategies, optimizing portfolios, and detecting market instabilities. Transportation, powering self-driving cars, managing air traffic, and optimizing logistics for goods delivery. Energy, designing efficient energy distribution networks and optimizing oil well placement. Governments, creating quantum-safe encryption for national security, securing communications, and planning resource allocation. The major challenges ahead. Despite the rapid progress, quantum computing faces significant hurdles before it can become commercially viable and widespread. Technological challenges. Current quantum hardware suffers from limited qubit connectivity and low gate fidelity, high error rates. Detecting, controlling, and correcting these errors remains a major scientific and engineering challenge. Cryogenic infrastructure. Most leading quantum computers operate at temperatures close to absolute zero, requiring massive, complex, and expensive cooling infrastructure to maintain. Lack of good software. Only a handful of quantum algorithms, like VQE, QAOA, and Shor's, have demonstrated a meaningful speedup over classical methods. Most real-world problems still lack a proven quantum advantage. Hybrid orchestration complexity. Integrating quantum subroutines into classical software workflows is incredibly difficult and requires entirely new programming paradigms and robust middleware. Benchmarking and standardization gap. There is no industry-wide standard for measuring and comparing the performance of different quantum hardware and software, which hampers objective evaluation. Vendor lock-in. Most quantum platforms use proprietary, non-portable software and APIs, making it difficult for developers to work across different systems and complicating collaboration. Collaboration woes. There's often a lack of deep collaboration and knowledge exchange between the industry developing the hardware and the academic institutions researching the core science. However, despite these immense challenges, quantum computing is poised to revolutionize industries by unlocking solutions to problems once deemed intractable.